Thanks very much, Tor, and thanks, Nico, for organizing this workshop. So, let's see if I can figure out how this works left and right. OK. So I'll just try and go forward. So the first thing I'll just mention is that we've just moved to Johns Hopkins, our lab, and we're recruiting postdocs. So please get hold of me if you're interested. The topic of the presentation is stimulus-locked network dynamics. And to give you a sense of the structure of the talk, I'm going to first talk about what they are, then I'll talk about why I think that they matter, and finally some considerations of methodological and practical considerations of if you want to map stimulus-locked networks. So what are they? So let's begin with this video that I really like. I think Randy Buckner made this movie when he was in Marcus Reichel's lab a long time ago. And it's just spontaneous data, spontaneous fMRI data projected onto the cortical surface, sped up by about a factor of 4, I think. And you can see this structure there. And this is what was so entrancing about the early days of when functional connectivity started to kind of blossom in the middle 2000s. People started to get interested in so-called functional connectivity, right? It seems like there's some pattern here, and that maybe we can capture some of this structure by looking at the patterns of correlation in these dynamics. So the first thing, the simplest thing that you can do is just say, well, I'm going to take one particular site on the surface of the brain, and I'm going to ask if it's correlated with another site. And thank you to Carl Friston, we call this functional connectivity, a term that hasn't always met with approval, but that's the name that we have. So we call this functional connectivity when two sites are correlated with each other in this manner. So we can correlate the seed site in red with all these different sites on the surface of the cortex, while someone is just lying in the scanner, for example, in the resting state, so-called resting state. And all the sites that are in yellow here are sites that might be robustly correlated with the seed. And we can call this a functional network, right? The set of sites that are correlated with the seed and correlated with each other. And I think that almost everybody in this room knows a lot about this, so I don't need to linger on this point. One of the reasons that people started to believe that this is not just junk, right? Because we always need to keep in mind the complexity of what we're measuring here and the way we're measuring it. One of the reasons that people didn't think this was just junk is because early on you could see that some of the sites that were correlated with each other were sites that you might expect to be functionally related. So bilateral auditory regions, sites that involved in attention, executive function, visual, motor function, etc. Now, one of the more recent trends in this area has been to ask, well, we saw these really interesting swirling patterns in that initial video. Maybe it's actually the case that these so-called networks are actually changing in some way over time, right? So people are interested in network dynamics. And this is just an example from a paper from Matt Hutchison from a few years ago, showing 4 different networks, 4 different patterns of covariation extracted from 4 consecutive time windows. OK. So we're interested in this, not only because it seems fascinating because it relates in some way perhaps to our own internal mental life, the way that it kind of moves over time. But also there are practical considerations here. We can potentially use this for diagnostic function in clinical settings, and also obviously for understanding cognition and so forth. All right, so there are some problems. So one of the problems is arousal, right? So Enzo Tagliazucci and Helmut Lauf showed quite pointedly a few years ago that if you look at some of the larger resting state data sets that are available, about half of subjects appear to be asleep after 10 minutes. So if you train a classifier, to go between sleep and wake, half of subjects are asleep after 10 minutes. This is a problem because sleep and wake have different patterns of functional connectivity. Another problem is breathing, and Gary Glover and Katie Chang have worked on this. So in the work that I'm going to describe a bit later on, this is something that we worried about a lot as well. And just to give an example, this is one subject's breathing data. And then this below is a kind of a processed version of the breathing data overlaid on the bold signal from the precuneus in the same subject. And this is the correlation, the cross-correlation. Right, so this is really chastening. If you're a person who's interested in cognition and you think you're considering the nature of situation representations or autobiographical memory or the self and so forth, and you're studying the default mode network, and one of the major nodes of that network shows that kind of correlation with a physiological confound, you should be worried. And one of the things we found when looking at this is that the magnitude of the correlation between bold signal and physiological regressors, such as this breathing regressor, is extremely variable across individuals. So you might have one individual like this, and the next one shows no correlation whatsoever. So it's also problematic from the point of view of individual differences, and you could also imagine that if breathing changes over the course of an experiment, that would be a problem. Right. So this is a problem. Another problem is motion, and so Jonathan Power has written a number of papers, and he's giving more talks at this conference on this topic. Okay, so just to summarize. Resting measurements allow us to map this repertoire of brain states, this continuous, beautiful, shifting repertoire of brain states, but it's difficult to tell signal from noise. So we know that our inner mental life is this wonderful, rich tapestry, but it turns out that the noise also can also be a wonderful, rich tapestry. And we want to tell the two apart. So this is where stimulus-locked networks come in. So functional connectivity is this thing that we can measure within a brain. You can see here the yellow seed voxel, and then the arrows pointing to other sites that you can correlate with that seed voxel. Now, we're going to merge this idea with another method called intersubject correlation. So intersubject correlation, the idea here is you take two different brains, and you take a particular region, let's say this yellow voxel, and you find that same yellow voxel in the two different brains, and then you present a common stimulus to those two different brains. And you ask whether the two different voxels in two different brains, the corresponding voxel in two different brains is correlated. And the logic is that if it's correlated, when a common stimulus is presented, then that particular voxel must be involved in some kind of information processing or processing of the stimulus. So what we do to map stimulus-locked networks is to combine these two ideas. Now we're going to take a seed, we're going to take my precuneus, and we're going to correlate it with your medial prefrontal cortex, while you and I are engaged with the same stimulus. And we're going to call that a stimulus-locked edge in our stimulus-locked network. So just to kind of hash this out a little bit, so we've got two different people, and we're going to take a set of ROIs or voxels, and we're going to have a time series for each voxel or ROI, and we're going to compute a big covariance matrix. So here's one matrix of n voxels and m time points. And normally what you do in functional connectivity is you would just take this matrix and multiply it by its transpose, or the transpose times the matrix. And what we're going to do is we're going to take the corresponding matrix from another person's brain. That's the only real difference. There is one other small difference, which is that if I correlate my precuneus with my MPFC, that's the same as correlating my MPFC with my precuneus. But if I correlate my precuneus with Nico's MPFC, it's not the same as correlating Nico's precuneus with my MPFC. Those give you different results. So you actually need to compute it both ways and add the two together and average them. And so you get this kind of correlation matrix that needs to be symmetrized in this way. Okay. And in this way, you arrive at a big covariance matrix, which is your set of n maps, n seed maps of this correlation across individuals, across regions. So just to unpack a little bit more of the logic, what we're kind of assuming here is that when you present a stimulus, you're going to measure this black X, this bold signal in one region, and you're going to assume that it's composed of these three different components. A stimulus-induced component in blue, some kind of intrinsic neuronal signal. So this is real neuronal signal. It's not a physiological artifact, but it just happens to not be stimulus-locked. And then there's this real noise, something else, physiological or something else, instrumental maybe. And when you compute functional connectivity normally, right, what you do is you take X from two different regions and you correlate them with each other. And the correlation between those two X's is going to contain a contribution between the correlation of all three terms: the stimulus-induced, the intrinsic, and the non-neuronal. Right? And that's kind of the issue, is that we don't know exactly how much is coming from each of those. So when you do it across individuals, the logic is, when I take an X and a Y, so two different brains, the idea is that the stimulus-induced component may be common across brains, but we assume that the idiosyncratic component and the noise component are uncorrelated across brains. So we can map a covariance pattern now that, in theory, should be much less affected by noise. Okay. So I'll just give you an example of what this looks like. So first of all, we just test the method and we'll say, what happens if I correlate two people's brains when they're doing the resting state, right? So they're both in the scanner, there's no stimulus, and now we just ask how correlated are two distinct regions in these two distinct brains. And the answer is, they are completely uncorrelated. So basically, if you do your stats right, there's nothing. There are 2 points worth mentioning here. Firstly, you need to crop the onset of your scans. Often there are transients, and it can be subject-specific, but sometimes there'll be these ramps that occur for 15 or 20 TRs at the beginning of a resting acquisition or even a task acquisition. So you could get some correlation across different individuals if they both had a common transient, but you crop those off. Also, it could be that people are gradually falling asleep over the course of your scan. So you might want to do a bit of high-pass filtering. But within the normal kind of bounds of what people do in pre-processing, you're not going to see reliable correlations across individuals at rest. Okay, so now you're going to present a stimulus, right? So the stimulus that we're going to present, the example that I'll show now is presenting this auditory narrative. It's a story called Pie Man, told by a storyteller called Jim O'Grady. You can listen to some of it. Let me see if you can hear it. Okay, so you can't hear it. That's fine. I'll read it to you. So I'm banging out my story, and I know it's good, and then I start to make it better by adding on an element of embellishment. Reporters call this making things up, and they recommend against crossing that line. But I had just seen the line crossed between a high-powered Dean and a pastry, an assault with a pastry. Okay, so there's the story. You're lying in the scanner, and you're listening to this auditory narrative. It's a very engaging narrative. And now we're going to ask, firstly, we're not doing networks, we're just going to do point-to-point, which voxels in the brain respond reliably across individuals to this narrative. Okay, and it looks kind of like this. So this is a set, this is about maybe around half of the cortical surface is going to give you an R value, maybe above 0.12 or 0.14 or so with about 11 subjects. So when you compute now a stimulus lock network, it obviously can only involve these voxels, right? So these are the sets of voxels that will respond reliably across different individuals to the same stimulus. And now within these voxels, you can ask about the between voxel correlation. Okay. So just to kind of unpack this a bit more, here's an example of what, if we take our 11 subjects, and we have in blue, we take the average of the first 6, and in red, we take the average of the last 5. And we just plot auditory cortex responses to this story. As you'd expect, you see pretty reliable responses. On the x-axis here is time, and then over time it's bold signal varying. And that makes sense. So there's some correlation across individuals in auditory cortex, also in precuneus, also in inferior frontal gyrus, and in IPS. So this is what we call inter-subject correlation. But when we talk about a stimulus lock network, what we're going to do is we're going to ask whether these different boxes are correlated, right? For example, the precuneus and the IPS are actually correlated at 0.56 with each other. And precuneus and IFG are anti-correlated, whereas precuneus and auditory cortex actually don't have a significant correlation. So this is saying that really, when I'm listening to this story, my precuneus really is correlated with your IPS, for example. Okay. So this is just an intro to say, what are these so-called stimulus lock networks? And now a couple of thoughts upon why I think that they matter and why they could be useful if you're the kind of person who is interested in mapping network dynamics or networks in your research. So the first reason that they matter is because they provide a more sensitive and reproducible tool for mapping networks. This in turn leads them to provide clearer links between brain cognition and behavior, potentially. And thirdly, this is something that is maybe still in methods development, but I think that in the context of people's interests in individual differences research, they also provide a potential route for overcoming anatomical variability. And I'll make a couple of points on that. Okay. So just to kind of give an example, imagine that in addition to that long story, to like a 7-minute long story that we present to individuals, we also present to them scrambled versions of the story. So we'll present to them a version of the story that is just a scramble of the words, totally permuted words. We'll take the sentences and permute the order of the sentences. We'll take the paragraphs in the story and permute the order of the paragraphs. So we have a range of different versions of the story which preserve different amounts of narrative context, effectively. Okay. And we're going to ask whether the networks are going to look different for these different stimuli. So, okay, let's start just using standard functional connectivity. So in functional connectivity, what we're going to do is, firstly, just at rest. We're going to take 11 subjects. We'll put a seed in the posterior cingulate cortex, and we'll extract this typical default mode network map during the resting state. And we'll average that map across individuals, and you'll see something that looks kind of like this. Now, we can compare this to what this map looks like. This is now functional connectivity within a brain. We can ask what that looks like when you're listening to the word scramble or to this intact narrative. And just to your eye, there's not a whole lot of difference. These networks actually are a little different, and you can, if you look closely, perform some kind of decoding that tells you which condition you're in, but it's not a stark difference. Now, if you look at a corresponding analysis using this intersubject method, what you see is that at rest there's no correlation. So you put a seed in the posterior cingulate and there's nothing. But there's actually a coupling of the default mode network that arises between individuals that is selective to the story actually being intact. So in other words, my default mode network is in some sense entrained to the narrative, and the nodes of my default mode network are actually entrained to each other in a way that is stimulus locked. Right? And that is only happening when I listen to a meaningful narrative. We don't see that for the sentence permutation, for example. We see a little bit for the paragraph permutation. Okay. So just to kind of unpack that in another way, we can just make a little network diagram. We can put seeds at most of the main nodes of the default mode network, and we can make a little network diagram with the size of the red circles indicates the correlation for that point to itself. And then the width of these blue edges indicates the amount of correlation between regions. And if you just look at these, they look similar, right? Okay, so the default mode network is the regions of my precuneus and my MPFC are still correlated with each other to a similar extent across all of these conditions. But if we compare this when we do the across-subject method, what we see is this method is really much more sensitive to the differences in the stimulus. And this is what you actually expect. You're changing the stimulus, and you're using a method which really tunes into the aspect of neural dynamics that are entrained by the stimulus, and it reveals it. Okay. So this is just what I call sensitivity. So this is saying that the method is sensitive. It is more sensitive to certain changes in the network state. It's also more reproducible. So what you see here on the y-axis of this graph is the kind of the amount of blueness in those little diagrams that I was drawing before. So it's basically the mean correlation in the default mode network. And on the x-axis here is time. And what you see is that there's a change over time within the story. So we take sliding windows within the story, and we recompute these networks, and we see there's a particular moment or kind of range of time in the story that produces the most robust coupling between my precuneus and your MPFC, for example. And we can replicate this in a separate group. So this is one group of 18 subjects in blue, and another set of 18 subjects in green. And we can also just vary the time window that we're using to compute this sliding window correlation. And you can see that even down to windows of around 15 seconds in duration, you can extract these network states that are pretty reliable, just in terms of the mean amount of coupling. Okay, so this is what I mean by being reproducible. So these sample sizes, I would say, are substantially smaller than what you would need to get this kind of reproducibility in a standard functional connectivity analysis. Okay, so because you have these slightly more reproducible states, you also are going to be able to establish a slightly stronger link to cognition, between brain cognition and behavior. So, for example, if we look okay, so here what you've got is that same curve I plotted before. So you've got that kind of mean coupling within the DMN on the y-axis, and then the x-axis is time. And the blue line is the intact narrative, and the other two lines are the two scrambled conditions. So you can see that it's really selective, this kind of gain in the story is very selective to the intact narrative. But it's not only the case that the mean amount of coupling in the DMN is kind of waxing and waning. It's also the case that the specific states are changing. So you might say, there's little numbers on there that I hope you can see, numbers 1, 2, 3, and 4 on the curve. So you might say that 1 and 3 have a similar mean DMN coupling. So the question is, what does the actual pattern of correlation look like at that time? Is it the same or different? So if we just look at point 1, we see there's a particular configuration of coupling at time 1, and there's a different pattern at time 2. And then we can look in our replication group and we can see that time 1 and time 2, again, have pretty similar change and pretty similar patterns in our replication group. But when we look at time 3, this just quantifies that these line plots are just vectors of the edge strength in the network, showing that the edge strength patterns are reproducible. But when you compare time 1 and time 3 actually have different patterns. So the time 3 pattern of edge strength is actually different from that of time 1. So this is starting to indicate that there are particular configurations of coupling that are specific to particular moments in the narrative. And if that's true, you should be able to do some kind of decoding, for example, right? And so you can do that. So you can build a decoder that either uses functional connectivity computer within a brain or a cross-subject method to extract a network and ask how well that decodes particular moments in the narrative. So we break the narrative down into 30-second segments, and then we decode which of these 14 possible segments were you in when you had that network state. And this is 18 different subjects, and you can see that the red line is decoding performance for using this inter-subject method, and the blue line is using the functional connectivity computer within a brain. So this is all just consistent with the idea that by computing the correlation across individuals, you can really pull out, you basically tune the analysis in to the stimulus lock component. So, okay. And finally, I'll just mention, I don't actually want to emphasize this too much because I think we need to replicate this, and we haven't replicated this yet, but if you measure memory, basically people's memory for different parts of the narrative, that coupling, that strength of default mode network coupling is correlated with moments in the narrative that are more well remembered. So if we have people do a fill-in-the-blanks test for exactly how well they can remember different parts of the narrative. I think we need to replicate this, but so there is a link to behavior here as well. Okay. Okay. A final point that I'll just mention, and again, this is, I think, a little bit less well developed, but I think it's worth mentioning. So in this time where people are very interested in individual differences, there's this kind of recurring difficulty with telling apart individual differences that are related to some kind of internal functional state from individual differences that relate to, let's say, how well your co-registration is working. And that in particular becomes problematic in clinical settings. And so one kind of approach related to what I've been talking about is basically functional co-registration. So either using hyperalignment or the more recent and substantially more effective method called shared response mapping. So what you do is you take multiple different brains and you assume that the response that you're measuring at a particular moment in a particular voxel is some kind of product of a feature, from an underlying feature space, and you map all the brains into a common abstract space. I'm not going to be able to go into this now because of time limitations, but I strongly recommend looking into this if you're interested in individual differences. And also, the one striking point I want to mention about what this method allows you to do is you can decode within a subject using this method better in the shared space. You can decode better in a common space than you can in the subject's own native anatomical space, because in the mapping to the common space, it actually denoises the signal. So I'm not able to get this enough detail, but I think this is a really promising avenue. Yeah. And there's a link, Cameron Chen's website has a link to a lot of the relevant papers. Okay. So I've said about what networks are and why they matter, and I've got a few minutes left just to say a couple of comments about how to go about mapping them. So I'm going to break this down into two choices: your choice of your stimulus and data set, and your choice of analytics and statistics. So the first question you might have is, why movies? Right? I mean, it's not, this analysis that I've described, you could have taken a one-back task, right, and just take the data from that and do this same analysis. There's no reason that you couldn't do that. And there are a couple of reasons why I think movies are a good choice. The first few reasons are just practical. Movies drive reliable responses in diverse areas. So if you only have 15 minutes and you want a kind of a widespread generic mapping tool, this is going to give you, so with a large number of subjects and a high quality acquisition, you can get reliable responses in about 65 to 70% of the cerebral cortex in a 15-minute scan. And let's say 20 subjects, 15-minute scan. So that's a good reason. So it's not too selective for one kind of subset of voxels. Another reason is that this is a delicate methodological point that I know less about than I'd like to know about, but it seems likely that the way that the brain operates around onsets is different from the way that the brain operates in more kind of steady state settings where it has an expectation of what's going to happen soon. And I think if you have a choice, if you want to map something like the endogenous repertoire of brain states, you'd rather be mapping the repertoire of brain states that are elicited in some kind of continuous setting rather than a state where it's kind of these continuous feed-forward onsets. Okay. And the third reason is that just watching movies makes people move their heads less. So that's okay. The more conceptual answer to this is, so coming back to this kind of video that Randy Buckner made, I think that there's a certain sense in which, paradoxically, this super complex stimulus, watching a movie, is actually kind of like resting state. Because perhaps our brains contain a generative model of the world. And what filmmakers have learned to do is to entrain that generative model and to drive it and guide it through a wide variety of states. And so this is speculative, so instead of having mind wandering in the resting state, you have mind guiding while movie viewing, right? So you still have this nice exploration of this kind of natural repertoire of states, but it's not, you're not being forced into one state or another. It's more like a kind of a push-pull between you and the stimulus. This is speculative. Okay. If you're going to be just making some choice, if you're interested in this and you want to choose a stimulus and data set, then you want to use audiovisual films because you want auditory and visual drive. You want films that have broad appeal because they need to be, a wide variety of subjects should be responding reliably to them. You want them to be engaging and energetic so people don't fall asleep, and also if you're dealing with clinical populations. You want them to contain spoken language. This is a bit more speculative, but it seems like a lot of the really higher order cognitive systems are more reliably entrained by stimuli that contain language. Why that is not totally obvious. Some rules of thumb, which you should disregard. You're going to get most of the SNR gain from these inter-subject methods that I've described. Once you have 20 subjects per group, you're going to be okay. You don't probably need more than that. And on the other hand, if you're interested in linking any of these network states to behavior, then you actually want really long scans because these distinct network states, if you're making behavioral measurements, the network states actually can switch quite slowly. You don't want to have super autocorrelated measurements. So if you want to have, let's say, 40 behavioral measurements in your experiment related to different parts of a stimulus, you would like to have maybe a minute of data for each of those. So you want long data sets if you want to link to behavior, to distinct behavioral characteristics or feature characteristics of the film. And there's okay. I've only got a few seconds left, so I'll just wrap up with some of the data sets that actually exist for this. There's the study forest data set, 20 subjects, 3,600 samples, audio only. There's the CamCan data set. It's a Hitchcock short film. It's black and white, audio visual, 649 subjects of varying ages, about 200 samples. There's a Sherlock dataset, which is BBC Sherlock, the first episode. Currently about 17 subjects, hopefully soon 50. It's 2,000 samples, and there's stimulus annotation available in the future. The data that I've been describing, some of it, 126 subjects across about 5 or 6 conditions and 200 samples each, audio only. This Princeton website that's linked here also contains a number of other naturalistic movie data sets that are suitable for this kind of analysis. Okay, I'm gonna have to really move through this quickly, but there are 3 rough frameworks that exist in the literature. One is kind of this correlation and covariance style of framework, and there's a list of papers that have used this. This is what I'm most familiar with. But you can also use so-called tensor ICA. It's a method that was developed by Christian Beckman and Steve Smith, and the group at University of Western Ontario, Adrian Owen and Roger Kusik, have used this with great success. There's also a method from Finland, which is a kind of a phased-based measure of interbrain coupling. So these are in the notes if you're interested. A final comment that I'll make, and this is related to some stuff that Bob Cox mentioned earlier. The statistics are actually a nightmare on this. Part of the reason for that is that if you have 5 different subjects and you're looking at one individual network edge, if subject 1 is correlated with subject 2 and with subject 3, then subject 2 and subject 3 have a kind of restricted range of correlation. So the different values are not independent, and that makes statistics much more complicated. And my general solution to this is bootstrap everything. And subject-wise, bootstrap is generally the best. And their papers are much more thorough and go into that in much more detail. So these 2 papers linked at the bottom here are the place to look. But a couple more general comments when doing this. Focus on large effect sizes. Always test out-of-sample reproducibility. And focus on the magnitude of your effects rather than absence or presence, right? I don't think it's really meaningful to talk about an edge being absent or present. If we're talking about coupling of dynamical systems, we have this rich coupling of all these dynamical systems in our brains. It doesn't really make sense to say that it's not useful to ask whether A or B are totally independent. The most important thing is to describe the kind of gradations of strength of coupling, I think. I think this is related to some other comments. Okay, just in summary, what are stimulus network dynamics? They're these networks that actually look a lot like resting state networks, but they happen to be networks that they have an anchor to a stimulus. They matter because they're more sensitive. We have a way of testing reproducibility for individual moments in a stimulus, right? They can be linked to cognition and behavior as a result. And just generally, as someone who's worked with fMRI, with resting state fMRI, there's a refreshing combination of having an anchor to a signal and yet also having the ability to explore kind of spontaneous, rich dynamics. Final, some credit to Erez Gemini, who pioneered a lot of the work that I described. And thank you to my lab, and thank you for your attention.
So I think this is fascinating, and it really seems to give you a way of reducing the confound substantially. Of course, you're also looking at something fundamentally different, right? You're only looking at stimulus locked effect. So I have 2 questions. One, how is this thing that you're now looking at conceptually different from sort of what drove some of the early motivation for looking at functional connectivity when it's this intrinsic dynamics of the system? And the second question is, how dependent are these patterns that you get that are distinct between states on the overall response of regions in the brain to those states? Would change the signal-to-noise ratio. Can you compare these patterns in detail? I mean, the decoding kind of goes in that direction.
Yeah, so in response to the first point, what are we studying, right? So there, empirically, the only thing I can say is that if we just take our same data set and we analyze it using functional connectivity or using this inter-subject measurement, if we cluster voxels according to their patterns of connectivity, you get very, very similar basically voxel clusters when clustering on functional connectivity or this intersubject. So there are some differences, and the paper kind of outlines where the greatest differences are, but they're surprisingly similar, which in a way indicates that what is happening, which comes back to another question about when you're seeing spontaneous dynamics, is it that, to what extent are the spontaneous dynamics really different from the dynamics that happen during task? Because you see the same thing in the kind of, in task cognition versus resting cognition, functional connectivity comparisons. They're surprisingly similar, as if there really is a kind of like a basic dictionary of states. There's also a model at the end of the paper in the supplement, which kind of outlines the nature of the signal-to-noise gain in a much more explicit way. It outlines the exact mathematical claim about the relationship between intrinsic and stimulus-driven. In relation to your second point, we certainly can't look outside of regions that are driven by the stimulus. On the other hand, when you have very large data sets, so for example, if you have 100 subjects and you average 50 and you average the other 50 and you correlate them with each other, at that point you start to get reliable responses in a very large proportion of the cerebral cortex. And I think I would kind of ballpark it that in about 3/4 of the cerebral cortex you're away from areas where you have to worry about just confounds of non-detectability of signal.